asleep. Thank you. So, okay, welcome to lecture number 2. First, question disclaimer. Remember that you can always ask questions now and whenever you want. So, do you have questions for yesterday's lecture about the tutorial? If you have doubts, don't worry, just ask. So lecture number 2, what you learn. Yesterday we saw how we get one detection and how we get parameter estimation for just one single source. Today, everything is going to be focused on the population. So we are going to see how the LIGO-Virgo collaboration does the population analysis given all gravitational wave events. Once we get this information, we will see how we can reproduce the results, if we are able to reproduce the results with our theoretical model. So we are going to explore how we form gravitational wave sources from first principles, starting from massive stellar evolution, binary evolution, and so on, and so on. Okay, so yesterday I showed you this plot. Again, we are doing population analysis. Another way to see exactly the same information is this one. So here what I'm plotting is the chirp mass, which is a combination of the primary mass and the secondary mass of each single source. So all the gray lines that you see, these are the posterior probability distribution of each single sources. The black line that you see instead is the observed distribution. This comes out from a simple KDE, kernel density estimation, probability density, the estimation. So what we want to do now is, given the observed distribution of the entire population, which is the thick black line that is showing this plot, what we want to do is to try to extract information from this population. And the way we do that is by hierarchical Bayesian analysis. So in the first equation, you see the posterior probability distribution of one single source. So P theta given the data is that I showed you yesterday that you know very well. Where you have the likelihood of the data given and the priors. What we want to do is like a step forward. What we want to estimate is that lambda. Those lambdas are the parameters describing the model, given all the data. So in the data in the curly parentheses means the entire set of observation. D1, D2, D3, D90 means all the observation that we collected so far. I'm going to talk about parametric models. So what we were doing is we're going to choose one specific model, and we are going to constrain the parameters of that models with gravitational wave observations. But there is like another big piece of literature that does not use parametric models. But I don't have time to discuss that. But keep in mind that I'm going to give references for that. And also because I think it's the easier way to understand how this analysis goes on with the parametric models. Okay, so what we need is to define the likelihood, as we did yesterday, but here we need to define the likelihood that takes into account all the data and provides you constraints on the parameters. And what you do is this. You have a product over all observation. You can do that because each gravitational wave observation is independent with each other. So you can, the probability of having the entire set of observation is just the product of each single probability. And each single probability is the thing I'm highlighting there. You have the likelihood of the single source, the one that I showed you yesterday, given the astrophysical model, which is this P theta given lambda. I'm going to describe that. I'm going to describe it later. So you see that integral, it is usually evaluated with a Monte Carlo summation. So that integral is substituted with this average here. This bracket operation is an average. where basically what you're doing is to use samples of the posterior probability distribution of the single source, and you substitute these samples in the astrophysical population and in the priors of the single source. This is what you do basically. So you have so the product goes over all gravitational wave detections that I'm showing here. So each line is one single gravitational wave detection. And each column is and each column are the parameters. So for example, primary mass, secondary mass ratio, effective spin, and luminosity distance. So what you do is to sample from these distributions, because you can do that. You already have done the parameter estimation of single sources, and you substitute the samples in this function here, P, the astrophysical population. So let's have a look of this astrophysical population. Okay, for example, the easiest model that you can think about is a power law, a truncated power law. So what you're saying is that the primary mass distribution of black holes is distributed as a power law given the two extrema. So basically what you're going to do is, so what you're saying is that the primary mass distribution has this shape, and the parameters of this distribution is this alpha, this minimum mass, and this maximum mass. This is the simplest case. This is the simplest thing that you can do. And what you're doing is to constrain these parameters, alpha, minimum mass, maximum mass, given the gravitational wave observations. So do you have an idea why a power law is like a good option? This is a question for you. Over there? Yes, did you understand the question? So basically massive stars, so we believe black holes, the black holes that we are observing come from massive stellar evolution. Massive stars, the initial distribution of massive star is a power law, the initial mass function is a power law. Of course, going from massive star to black holes, a lot of things are going to happen, and this is like the topic of this lecture. But you can think that in first approximation, the mass distribution of black hole follows the shape of the mass distribution of massive stars. Is this clear? Yeah. This is topic of lecture number 4. we are adding layer of complexity to the thing. So, a power law, the simplest thing that you can do, but you can also complicate things. So, for example, what you can do is to consider a broken power law, because what happens basically is that you observe the distribution of data. You see that it's not like a sharp power law. There are like things happening, for example, breaks, peaks, and you try to add to your model these breaks and peaks to actually fit your model. Basically, this is what is done. For example, here a power law plus peak, it means like a power law and a peak, a Gaussian peak, because you want to relate these features of the mass distribution with astrophysics. And this is going to be done later in this lecture. Or you can do a multi-peak, where you add other peaks to the power law. So basically, the idea is you get a power law, and you try to add features to fit it in the data. Because you want to, and the objective is to learn the parameters of this distribution. And then the thing in the denominator are the selection effects that we discussed already yesterday, where you saw that basically at high distance you don't see sources. You want to take in account selection effect. Selection effects are a property of the parameters. So you see that they depend only on lambda. So basically, what you're saying is that, for example, if you assume the power law, mass distribution of black holes, you are already saying that you're not seeing the like for example the small black holes in a way, like the hmm? You mean those that distance? You mean? Yes, sure. But this what we are doing here is to look at astrophysically formed black holes. So if you are like basically you assume that these black holes, so for example in the truncated power law, you're assuming like a minimum max and maximum mass. So you're looking at a specific max spectrum of black holes. You're not going to like the super small black holes that you form primordially. Also because they are too distant to observe with LIGO. This is going to be important with Einstein telescope though. So selection effect is going to be, again, lecture number 4. But in your, so just keep in mind the fact that selection effects takes into account that your detector is not perfect. Your detector is going to miss some sources. You want to counterbalance this thing. Okay, so results. If you are looking at masses, what you can get from the last published analysis that takes into account the GWTC3, the gravitational wave transit catalog number 3, the last one of 3 years ago almost. You get this. So in this plot, you see the primary mass distribution. The one that was constrained with GWTC3, the blue line with the shaded area, and that was constrained on GWTC2. On the right, instead, you see the mass ratio, so the ratio between the two masses, and again, compare what was done during GWTC2 and what was done during GWTC3. So you see that what basically changed between these catalogs is the number of sources. So if you have like higher number of sources, you can constrain better your distribution. This is trivial. Here I am highlighting this Gaussian peak. So basically what was done was to inject this Gaussian peak in the model. And what you want to do is to see if your model is going to basically like if you inject the Gaussian peak, but then the Gaussian peak disappears once you made the model see the data, then you see, okay, the Gaussian peak is not there. But if the Gaussian peak stays there, it means that your data are supporting the Gaussian peak. And this is very nice because this Gaussian peak is connected with astrophysical processes that you're going to see later on. Questions? Yes. So you don't understand this plot? So that is the mass ratio, so the ratio between the primary mass and secondary mass. I didn't get your problem. So yes, but also the shape of the mass ratio. It's all right. I got it. I got you. Also, you might ask why you have this shape of the mass. Why you have like more support of mass ratio equal to 1. The answer is the same as the one before, because massive stars tend to pair up, and the mass ratios tend to be equal to 1. So the two stars tend to have the same mass. So this is something that you observe. The questions? Is it clear? Okay. Spins. Let me introduce spins because this is it's a tricky matter in gravitational waves. Because as I told you yesterday, spins are you have two vectors basically, and so basically 6 components. What it usually done in gravitation, like in this type of analysis, is to define two combinations, chi-f and chi-p. the meaning. So basically, chi-f takes in account of the distribution of spins along the angular momentum of the binary. You can see, so for example, this is the angular momentum of the binary, and chi-f is the projection of the, so it takes is a combination of the projection of the zeta component of the spins along the angular momentum of the axis. Chi-p instead is the other way around. It takes in account, is a combination of the spins along the perpendicular direction of the angular momentum. And we define these two quantities because they are approximately conserved over long period of times during gravitational, during the gravitational wave strains over time. And they are very, very, very handy in a way. So basically, chi-f takes into account the, so yeah, chi-p, so if you have like a non-zero chi-p, it means that your spins, you have like a non-zero precessing orbit. So you can actually see that in the gravitational wave strain that I showed you yesterday. So this is the result that you get from gravitational waves. So on the left you have chi-p, so that takes in account of the component perpendicular to the angular momentum, so the precessing orbit. You see that between the two catalogs, GWTC2 and GWTC3, you are actually constraining much more better the chi-p distribution. And it's close to 1, so the median of the distribution is close to 1, but it's not 0. So you have a component of spins that are actually perpendicular to angular momentum. And the same thing you can say with chi-f. Again, like more detection constrains better the distribution of the spins, and the take-home message from spins is that they're small, but non-vanishing. So we have spins. They're small, but we have spins. The rates. The rates are of prominent importance because this is also the topic of my PhD thesis. So the rates. So what are the rates? Basically, what you want to measure is the total number of sources, the total number of merging sources. So it is the quantity is like number per gigaparsec cube per year. So also this quantity is also called merger rate density. So the number of rates. So you take like a volume of our universe. You count the number of sources that you have, and you want that to be a rate. So like a number varying with so like a number given time. So in the LIGO analysis, what they do is to model the rates as 1 plus z to the k. 1 z is the redshift, and the result is that you see on the left panel. So basically, what you see is that the rates are increasing with redshift. Do you have an idea why this happens? So basically, from this analysis, if you go from redshift 0 to redshift 1.5, you have more mergers of black holes at redshift 1.5 than now at redshift 0. Do you have an idea why? You mean the volume? So because you are taking like a bigger volume? No, I don't. So yes, you are considering a bigger volume, but what you do is actually take like a redshift being. So you are looking at redshift 0, redshift 1, redshift 1.5. So you're looking at a shell of the universe in a way. It's not that they integrated the redshift, they integrated merger rate over redshift. So you say, that is a matter of masses of the black holes. Maybe? Or
If you spread the mass of I don't know, of a supermassive black hole into a bunch of stellar massive black holes, you have if those black holes merge, you have a bunch of more events than if two massive supermassive black holes merge.
I think the discussion is going a bit too wide. Try
Yeah.
to focus, Filippo.
Maybe it's just,
The discussion is running
no,
wild.
but I like it. I mean, on my side, I like it. So
that's an effect. I don't know if it's relevant.
no, I'm not saying it's wrong. But I want you to think about stars as we did with the initial mass function. So the distribution of the distribution of initial mass of massive stars is a power law, and you got that. And I want you to think about stars again. What is plotted here is also the star formation.
So I'm guessing in the past, IMFs were more top-heavy, and then you're forming more black holes. Maybe that no.
This is true, but you need to go back to a way higher redshift 10 to get top-heavy IMF. No, the reason is that our universe was producing more stars back in the days than now. But the universe was more efficient in producing stars. The star formation rate was higher at higher redshift. And the thing that we are looking here is that the rates of black holes follows pretty well the star formation rate. The star formation rate is the dashed line in that plot. So what is happening is that the measured rate is it's over there. It's all right. The measured rate is what we collected so far is that the measured rate is tracing the star formation rate, and this is like something that might be trivial in a way now that I said to you, but this wasn't granted like before having this measure because depends. I mean, it depends on how black hole forms. If they form from stars, well, it makes sense. But if they are, for example, primordial black holes, there's nothing that tells you that they should follow the star formation rate. Yeah.
From star formation to coalescing of compact object, there is a long way. There are billion years. No? So the effect of the delay should appear there and should include.
The effect is sure, but as I'm going to show you in a while, we have astrophysical process that speed up this and they contract this delay. So the black holes tend to form and merge in a dime.
There's some assumption that could be not true. Look at probably in the first time of the universe, we have not only one bump of formation, but several bumps. So stellar formation is quite complicated, I mean, because you have to assume many things, like, you know.
We're going to discuss star formation rate tomorrow.
We cannot discuss this question now. We don't know about tomorrow, because if the star formation is only one single event, the IMF is one way. If you have two, you know, phases of star formation, you have another kind of EMF in the future, so it's connected.
They are. So the star formation rate is like so you see that they plotted arbitrary normalization. What?
No, also for the range of LIGO, you have effectively only one peak of star formation, because the ones that are farther away, you do anyway, are irrelevant for LIGO. But for third generation, it might be different, as Filippo will
Okay. So plot on the right instead is the posterior distribution of K, the power index of that model, and I want you to see that the mean of K is shifted toward right. So with GWTC3, with the last catalog, we are able to say that at 99% credibility, K is larger than 0. So the rate is increasing, and this is like a striking result from the last catalog. And probably this is a lie. I don't know if this is going to be your today's hands-on section, but you're going to evaluate the rates given models of black holes. So you're going to model your star formation rate, you're going to model your black holes, and you're going to combine these things to predict the merger rate density from theory. So this is observation. In your hands-on section, you're going to do that from theory. So, and you want to, of course, try to match them. Okay, so that was from observation. Now, finally, we go to the point how we model astrophysical compact objects. So how we can ask, can our models predict actual observation? And so now we need to open this new chapter. So let's talk about this compact object. We have neutron stars and black holes, as I told you. So neutron stars mass is between 1 and 3 solar masses. If it is, you need your neutron star to be above the Chandrasekhar mass, which is the maximum mass star for supported by electron degeneracy. And you want your neutron star to be below the Tolman-Oppenheimer-Volkov limit, because if it is above, what you have is not a neutron star, but is a black hole. Now, between these two, especially between the Tolman-Oppenheimer-Volkov limit, you need to take in account, you need to fix the Newton star equation of state, which is unknown. I mean, it's one of the scientific goals of gravitational wave detection. Black hole mass have a mass larger than 3 solar masses. So this is like the ranges. Okay, so you want these two objects to be in a binary system. So you want them to orbit each other because you are measuring this. So you're measuring the moment that these two things merges. So what you need to take in account is gravitational wave decay. So your binary system is emitting energy given gravitational wave radiation. And what you now I want to prove my point, but and I want just to explain you very quickly how you get the basically how you model the gravitational wave decay. So what you do is the Frankenstein monster again. You couple Newtonian dynamics with gravitational wave radiation, and this is what you get from gravitational wave radiation. So if you take in account Einstein equations, you do the calculation, you can go to Peters 1964, so it's a quite old paper, but you get all the calculation if you're curious. What you put the number, you do a bit of math, you get this. You have the orbital decay, so you get the A is the semi-major axis of the binary, so the distance between the two sources. You have you have the given gravitational wave radiation, the binary system is shrinking. And what happens also is circularization. So as you emit gravitational wave, your binary tend to circularize. So tend to be, so these are the two things happening with gravitational wave radiation. You can evaluate those two equations and you get this. So in this plot you have time over the x-axis and the separation on the y-axis. So like what you can do is to fix the separation and you fix the initial eccentricity. And I want you to focus on this thing here. This is the Hubble time. So like the time that goes from here to here is the age of the universe. So this is saying to you that not all compact objects can merge due to gravitational wave radiations. For example, these compact objects here that have like, their merger time is longer than the time of the universe. Another way to see this is to, you can integrate the the semi-major axis equation, and if you fix eccentricity, you can have like a closed form of the time that needs to emit gravitational waves. And it depends on the initial semi-major axis, of course, as I showed you before. The masses of the two compact objects, so more massive tend to be like, you have like shorter time for the two compact object to merge. And if you do like a simple, if you crunch this number, so you take into account like a neutron star with one solar mass separated at one astronomical unit, which is the distance between Earth and Sun, so quite close, you get a time of merge of the 10 to the 17 years. So like these two neutron stars separated by the distance of Earth and Sun, they're not gonna merge due to gravitational wave radiation. So you need astrophysics. This is the point I want to prove. You need astrophysical process that make two compact objects merge together. Otherwise, for most of them, either they bore like super close, or they're not gonna merge. Questions? Yeah. Yeah. So now we are going to see what astrophysical processes had them to merge. Yes, sure.
When they get closer, this approximation breaks, like it doesn't work.
Sure.
So like, how do you know that this will also work like when they get near? So we're only looking for the ones that like are above the Hubble time.
Sure. No, but post-Newtonian approximation, I think breaks when they are few times the Schwarzschild. Can you help me?
Okay. Oh, same when they are close enough so that the approximation doesn't work. Like we would be in the case that it would be the gravitational wave decay is enough to make the merge. So we are not looking like when they're this close.
Yeah, for example, in this plot here, the initial separation is way larger than the Schwarzschild radius of the two sources, right? So you can go ahead with post-Newtonian approximation.
Okay.
Of course, when they are like few times the Schwarzschild radius, at that point you need numerical relativity, because at that point you need to solve Einstein equations. They are not nonlinear, and you can do you can do post-Newtonian, and you can do like closed form. But this is something that you need only when the two sources are already very, very, very close. Here we are talking about that you put like sources like at a reasonable distance, what we are looking at is to how we can make them merge from astrophysical processes.
Okay.
Questions? Simple. Okay. Okay. So now astrophysics. So as I already said, black holes and neutron stars are the final outcome of massive stellar evolution. So we need to focus now on single stellar evolution. So let's see what are the astrophysical processes playing a role once we look just at the single star, not in the binary system, just one star. So the most important parameter that we need to consider is metallicity. That was we already talked about that yesterday. So just to remind you, metallicity is the fraction of every element heavier than hydrogen and helium. So it's a fraction, it's a number between, 0 and 1, but just to give you like a reference number, the sun has a metallicity of 0.02, and it is a metal-rich star. The other effect is that is connected, of course, with metallicity are stellar winds. So what happens basically is that photons in the stellar atmospheres couples with ions. You have like a scheme over there that explains to you what happens. So photons coming from the star interact with ions. What basically happens is you have the transfer of linear momentum between the photons and the ions in the stellar atmosphere, and so basically these ions can unbind. So what is happening is that the star is losing mass due to stellar winds. So why metallicity plays a role? Of course, if you have like bigger ions, you have higher chances that your photons interact with these ions. One of these are called line-driven winds. So basically, because your photons are interacting with specific spectral lines of your ions, for example, of iron, oxygen, especially iron. So you can find a relation between mass loss and metallicity of the star, which is that one. So this is like the mass loss per unit time. It is proportional to the power law of metallicity, and this power law, of course, depends on the stellar system.
Okay, for the proportionality to metallicity, but what's the time scale of this mass loss? What is the pre-coefficient?
It's the plot on the right. So in the plot on the right,
no, but what it depends physically? I mean, how can I estimate the coefficient? I mean,
how you can estimate the coefficient?
What I mean, the time scale is mega year, but what fixed the scale of the mega year? Is the cross section for absorption of the photons?
So I mean the time of things. So the time on that x-axis is the time of evolution of massive stars. So it depends on like on the nuclear burning rate of the star, but this is not what you're asking.
The mass loss is related to the absorption that give rise to the solar wind, no?
Yes.
So, okay, maybe I can ask you later, what are the parameters that entered that cook up the mega year? But again, no, this m dot is basically 1 over mega year times m. I read it from there. How does the mega year comes out? Okay.
Yeah, I need to look at it. I think I cannot answer to you like now. So, but what I want to tell you is that massive and metal-rich star can lose up to 50% of the initial mass due to stellar winds, and this is something that you can see in this plot. So what we did was to what they did was to taking like a massive star, a 19 solar mass star in the zero age main sequence. Same star with different metallicity. So you see that if you take into account solar metallicity, again metal-rich star, basically your star at the final end of its evolution lost almost 50% of the mass, and this is of course has an effect on black holes. This is the plot that I want to show. Basically, what you see here is the initial mass at the zero age main sequence on the x-axis, and on the y-axis you have the final remnant. So it can be like a neutron star or a black hole. So that I put like a line which is like a no wind limit. So if you could like switch off completely no wind, you have like an identity function. So all the mass of the massive stars ends up in the black hole. But this is not the case, of course. For example, if you take in account this 2 to the minus 2, which is like the solar metallicity, 0.02, you see that the massive star, like the final remnant, doesn't go up much. So basically, what I want to show here is that stellar winds set the maximum limit of the black hole mass. Metal-rich stars cannot give you back massive black holes. This is the take-home message of this plot. Okay, that was the most important thing about single stellar evolution. But if we want two black holes to merge together, they must be in a binary system. Fortunately for us, observations tell us that massive stars tend to be in binary system and also in multiple systems. So they can also be like in triple system and so on. So in this plot, I'm showing you the primary mass of the star. And on the x-axis, on the y-axis, you have the multiplicity. So like the fraction of stars that are in a system that is a binary, at least a binary. And the spectral type on the top gives you a suggestion of how massive the star is. And you see that B and O star tend to have like a high multiplicity. So from observation, we see that massive stars, that are those that are interesting for us, that because they are those that produce black holes, tend to be in binary systems. So this is a good thing. So binary system is a good place to form and merge black holes. Questions? Yes, sir.
I mean, are tripole and high order multiplicity in common? Tripole and...
I mean, from this plot, I think the picture is pretty clear. Unfortunately, we do not evolve like triple system in our codes because the evolution is much more complicated. But they are. I mean, yes, multiplicity and triple and high order fractions of system. Yes.
No, but I mean, what is the ratio of triple compared to double? Say?
I don't know.
Okay.
I don't know. I really don't know. No, this is like the integrated fraction, like at least two systems. Yeah, 70% of massive stars tend to be in binary systems. Okay, so let's take into account these formation channels, the so-called, sure.
I'm not pretty sure about how the black holes form in these systems, but it is the possibility of losing the companion star when one of them die, like in the explosion or something like that. The other one leaves or get...
Yeah, you can do that in the dynamical formation channel that I'm going to explain you in few slides, because you need that your binary system interacts with another body. So in this formation channel, we are considering two binary systems just interacting with each other. So we are not considering other interaction.
No, but I think it was considering the supernova explosion might disrupt the binary.
Ah, yeah, sure. Yeah. I'm sorry, I didn't get the question. Yeah, you have the binary so the binary system can be disrupted. The phenomenon is called the supernova kick. So basically, the explosion of a supernova is not symmetric. And this asymmetry produces a kick that can also destroy the binary. Unfortunately, I'm not talking about this phenomenon, but it can happen. And it can happen especially with neutron stars that can disrupt the binary because they are like less massive than black holes.
But it shouldn't affect it. I mean, it's probably a sizable fraction, but it's not the majority.
It depends on the magnitude of the kick, which is unknown. So what we do is to observe neutron star systems in our galaxy, because I mean a lot of neutron stars that we observe in our galaxies do have a velocity, so like a non-zero velocity, and this comes from the kick of the supernova that generated the neutron star. So what usually we do is to take in account that distribution of velocity that we observe, and we sample the supernova kick from this distribution of velocity. But I can tell you more about this. Do you have a question over there?
Filippo, could you show the previous slides, please?
This one?
For a given spectral type, we have 2 points, upper and lower points. What's the meaning of the 2 points, the upper and
I think this is exactly the question that Ricardo just asked me. Yeah, this is the so this is So B means binary system, T tripole, Q quadrupole over single. Yes, this is the question to answer. Thank you for asking the question that allowed me to answer the previous one. So basically, this is, so the thick line is all the systems that are at least in a binary. So binary system tripole over single binary tripole. And THF is the fraction of from tripole on. So this is, and of course, uncertainty.
Exoplanets are formed in the left low side.
Mm-hmm.
So at some point you can figure out how many stars, planets form in these two models. So that is funny because you have no resolution, but in the left is the planets, just before the broad dolphins. And the two lines started in different ways. Have you an explanation why you have these two so different?
I have no idea. This plot comes from this this reference. We can have a look at it, but I have no idea.
Looks like two different scenarios, right? The upper and the low scenarios is quite different.
Yeah,
So
I agree with that, but I have no idea. I have no explanation. Okay. So isolated formation channel. I think we need to speed up a bit. So basically, yeah, two stars form from the same cloud of gas, and this can happen from the plot that I showed you before. And then they finally produce two black holes that can merge together, or two neutron stars that can merge together. In this formation channel, we have two main processes, the mass transfer and common envelope. So on the chart that you see on the right, you see the two massive stars in the main sequence, MS means main sequence, orbiting each other. The first thing that can happen is the mass transfer in the Roche-Lobe overflow. It's going to be clear in a second. Production of first black holes, and again, you have the other star still in the main sequence. Common envelope evolution, and then you can ask, is the common envelope ejected? If yes, you have a black hole in the core of the other star orbiting each other that can actually produce the two black holes that can actually merge. So this is the general idea of this formation channel. You have like two massive stars, mass transfer, common envelope, like in the simplest possible way. These are at least the two main processes that you need. So mass transfer due to Roche-Lobe overflow. First thing that we need to define is this Roche-Lobe. So on the plot that you see on the right, you have a depiction of this Roche-Lobe. So you have like you are looking at the binary system from the top. So the thick line that you see, the thick line that is this thick line here is the Roche-Lobe, which is like the a definition of the equipotential. I put there the equation that defines the Roche-Lobe, and you see that it depends on the separation of the two stars and depends on the mass ratio. So what happens is that you have the one star that that gets bigger because of single stellar evolution. This is what you saw yesterday, the star going the red giant branch, supergiant branch, and so on. So it gets bigger, and it can fill its Roche-Lobe, its Roche-Lobe. When this happens, you have you have mass transfer due to, via L1. So L1 is the first Lagrangian point, this one. So basically what happens is that the mass is transferred from one star to the other. And when this happens, when the mass transfer is stable, so the other star is accreting mass in a stable way, what happens is that the orbit shrinks. So mass transfer helps you to shrink the orbit of the binary system, and actually boost your probability to merge. Common envelope. I want to show you a GIF that explains to you what happens in the common envelope. Yes. Can you see it? Okay. So basically you have the massive star, so the red star, that is getting bigger because of the single stellar evolution I just told you about. It fills the lobe overflow. Mass is transferred to the other, but in an unstable way. So the other mass is not able to accrete the mass that is coming from the other star. So what happens is that the massive star that is losing mass basically engulfs the entire binary system. So this is the so-called common envelope phase. So what you have is, for example, an already formed black hole, a core of a massive star that are rotating in the same envelope. And this is very important because this basically allows the binary system to shrink further. So the common envelope is another engine that allows you to shrink the binary system. And the most important question is, does the binary survive the common envelope phase? Because it can shrink a lot, the binary system, and what you can have is that the already formed black hole and the core of the massive star merge together before forming the binary black hole, so the black hole binaries. You might ask why the binary shrinks. I didn't tell that. So basically, what you have is a drag force between the two cores and the common envelope. So how we model the common envelope? This is like the most important question at this point. So you can either use hydrodynamical simulations where you have the two cores orbiting in the same common envelope, but this of course takes a lot of time, as any hydrodynamical simulation. Or you can use the so-called alpha lambda formalism, which is a formalism that helps you to model the common envelope in an analytical way. And I'm going to tell you what you do. Basically, you have the binding energy. The binding energy of the envelope of one stars with the core of the core of the. So basically, what you have is what you want to equate is the binding energy of the common envelope and the loss of orbital energy of the binary system. So this is what you want to do. This is the operation that you're doing. The binding energy, so the binding energy between the core of the massive star and the envelope of the first star, the core of the second star and the envelope of the second star. So you do that. You do that, and basically what you get is this equation here, where you have this alpha parameter. So this alpha parameter is called the common envelope ejection efficiency. So we do not know the details of the hydrodynamical simulation in this case. So what we want to do is to introduce these two free parameters, the alpha and lambda parameters. So lambda depends on the evolutionary stage of the massive star, while the alpha parameter is a free parameter. And basically, it tells you how efficient is the common envelope to shrink the binary system. Was I just ask question if it's not clear? Okay, so but can we explain all observation with only the isolated formation channel? Yes.
Can you go back the previous slide, please?
Yeah.
So, I mean, in the situation there, when there's a black hole and the massive star and one envelope. I don't really understand, like, what are the two envelopes in the first formula?
You don't have one of the two.
Okay.
I mean, it's one that, like, the binding energy is 0 in that case. So this is like the general case where you have, where the common envelope happens when you have the two stars with the two cores, but of course it is simplified if you have like one black hole, it's just the envelope of one star. So you eliminate that factor.
And the dynamics of this envelope being ejected, you only really get that from the hydrodynamical simulations. Otherwise, you have to introduce these parameters to describe it.
So, yes. So basically, this is when you equate the binding energy with the loss of orbital energy, you are saying that you are asking yourself how much energy I need to take from the binary system to eject the envelope. When these two things are, and you equate just these two quantities. This alpha lambda formalism is used in population synthesis simulations, which is what we are going to discuss in lecture number 4, because it allows us to follow the common envelope phase with just 2 equations. Because, of course, running hydrodynamical simulation. But there are, of course, works that try to that make these two these two approaches to talk with each other. So you can run an hydrodynamical simulation and ask yourself what is the alpha parameter that I can get from the hydrodynamical simulation. Okay, so the question of this answer is yes or no? No, clearly. Because we have another effect, the pair instability supernova. So what happens in very massive stars with helium core of above 64 solar masses, you get like super high temperature in the nucleus of the star, and basically you have an efficient production of gamma ray radiation in the core of the star. Gamma ray photons scatters with atomic nucleus, and this produces electron-positron pairs. So in this phenomenon, what happens is that you are reducing the number of photons in the nucleus of a massive star, and this results in missing radiation pressures. So basically, the nucleus of the core missing radiation pressures, this produces dramatic instabilities, and the core starts to collapse at the point that it is not leaving remnant. And this defines the so-called pair instability mass gap, which is like a hot topic, I mean, in the current gravitational wave interpretation. So you have, let's take into account the blue line where you have like, this is again the initial metallicity. So if you follow the blue line, so on the x-axis you have the mass of the stars in the zero-age main sequence. If you follow the blue line, you see that on the y-axis you have the remnant. You find that you end up with having no remnants in this pair instability mass gap. You can have again remnants, but you need to be like super high massive systems. Like the massive star must be like above, in this case, above 200 solar masses.
The Y scale, where is located the gap? Because you're missing the
yeah, now you see the. So I'm going to that point. So you define this pair instability mass gap because of this phenomenon. And here you have the y-axis. So the y-axis you have the remnant. What the LIGO-Vigo collaboration plotted here are gravitational wave systems, detected gravitational wave systems, and you have this system here, GW190521, that is sitting exactly in the pair instability mass gap. So gravitational wave observation, this gravitational wave observation tells you that isolated formation channel does not work for any gravitational wave observation. Because, so in this case here, you have that the primary mass falls in the peri-instability mass gap. So the two dots here, they fall exactly in the peri-instability mass gap. And the final black hole, the red dot, is an intermediate mass black hole, because that black hole there has a mass that is above 100 solar masses. So you talk about stellar mass black holes below 100 solar masses. Between 100 solar masses and 10,000 solar masses, you're talking about intermediate mass black holes. And so this was a striking event, because puzzled us a lot. And just to explain this single event, we needed to take into account other formation channel. And this is the dynamical formation channel, where we also take into account of interactions. I will be very quick, because Alessandro is going to talk about it extensively next week. So about what this formation channel takes place, where the density of stars is above 10 to the 3 stars per parsec cube. This happens in globular cluster, nuclear star cluster, and young star clusters. And also these places are like an environment of formation of massive stars. So in these places you have massive stars that can generate black holes, and this massive star can interact with each other. So the dynamical formation channel introduces a lot of processes. The first one is hardening. Basically, you have two black holes in the same binary system, and a star interacts with the binary, and extract binary energy from the binary system, and this shrinks the black hole. So this is another phenomenon that allows you to shrink the binary system and to boost the probability of the two black holes to merge. Exchange instead form binaries of black holes. For example, you have a black hole interacting with a binary with a black hole and a star, and the black holes take the place of the star. So this is a way of forming new binaries of black holes. And if you pair up these two, if you combine these two processes, you can end up with hierarchical mergers. So like subsequent mergers of black holes, where you have stars that extract binary energy from the binaries. The black holes can merge. Black holes another black holes can take place of a star, and then you can end up with another binary system that can merge again, and so on, so on, so on. This is the hierarchical formation channel. I'm running late, I think. No, I mean, tell me what to do.
You can have surely 15 more minutes.
15?
15, 1-5,
okay.
15.
Okay. Questions?
No, but you're suggesting that the remnant of a coalescence can be recycled?
Yes.
But how often? Can you estimate how often?
This is a huge topic.
Yeah, I mean,
it depends.
It's non-trivial to estimate the rate of this.
It's not easy at all. So it depends. Two things. First, when two black holes merges, you have relativistic kick. So they merge, so similar to the supernova kick. I mean, completely different physical process, but similar to the supernova kick, the two black holes merge together, and from general relativity, you end up with a kick. So the remnant black hole can escape the system. That can be the globular cluster, nuclear cluster, and so on. And then the probability to pair up with another black hole depends on the density of the system in which this black hole is. So if you have like loose system, this probability is lower. So, but actually, the question to your answer is depends. Depends on the system in which the black hole is the subsequent mergers of black holes is happening. When we treat field binaries, we do not, so This is 0, of course. Field binary is 0. You must be at least in a cluster.
Or maybe close to an AGN.
Oh, yeah, in an EGN, again, this is an environment that hierarchical mergers can happen, yes. Runaway collisions, instead, is process that it is important because it can explain a black hole's independent instability mass gap. So what happens in a cluster is this phenomenon called mass segregation, where the massive stars tend to accumulate in the core of the cluster. So the probability that two massive stars merge with each other is higher in the core of the system. And what happens is that you can end up with a massive star that does not have like a massive helium core, because the pairing stability supernova depends on the mass of the helium, the mass of the core. So this massive star can evolve and can produce in a black hole that is in the pairing instability mass gap, because you are because of this merger of massive stars. Okay, so now that I showed you that at least we need two formation channels to explain gravitational wave observation, you might ask, is there a predominant formation channel? Like, is one of the two is contributing more to the formation of black holes actually observed by LIGO Virgo? What you can look at are signatures. So, for example, what I'm plotting here is the chirp mass, the mass ratio, and redshift and chi-effective spin distribution. The red line is black holes formed in the isolated formation channel. Blue line is black holes formed in the dynamical formation channel. And you can already see the difference. You see the difference, for example, on the chirp mass, that you end up with having a tail of more massive black holes in the dynamical formation channel for the process that just you described, hierarchical merger, runaway collisions. And the other striking difference is about chi-effective. So where you see that in the dynamical formation channel, chi-effective is exactly on 0, while in the dynamical formation channel, this is not true. You have like a non-zero component of the chi-effective. So if you look at properties, do you have a question?
Right?
Huh?
You just say that the dynamics is not centered, but you wanted to say the opposite, I guess.
What did I say?
That the dynamics is not centered and the dynamics is also centered, I think. Well, probably a lapsus. So the dynamics is the one that's centered at 0, and
yes.
the isolated one is the one that's centered at 0.2.
Yes.
Yeah.
I say the opposite. I'm sorry.
Yeah.
I'm sorry. So if you model your black holes either in the isolated or in the dynamical formation channel, you see that the two populations have different signatures. So you can ask yourself, can we evaluate a mixing fraction? So you want to have an idea if you have a predominant formation channel. To evaluate a mixing fraction, you use, and now I'm trying to close like a circle, you use exactly in the same likelihood that I showed you before, where your parameters lambda is one of your parameters lambda is the mixing fraction. So the astrophysical population that you're modeling is simply the sum of the astrophysical population coming from the isolated formation channel and the astrophysical population coming from the dynamical formation channel. You sum them, and what you want to infer is this F. So you are going to use Bayesian hierarchical analysis to infer properties to constrain this F. And the result you get is the one that I'm showing you on the right. So you have the mixing fraction. So if the mixing fraction would peak to above 0, it means that all of your black holes come from the dynamical formation channel. The opposite if it would be peak on one. And here you see three different curves. You see this blue one that is favoring the dynamical formation channel, green one a little less, and yellow one a little less again. And the difference between those three lines is this sigma 0.2, sigma 0.4, and sigma 0.6. Now you might ask, what is this sigma? This is the hands-on section. So, so if you it could be today or tomorrow, whenever, when we will have our hands-on section, we will understand the meaning of that sigma. But basically, it defines the distribution of metallicities. Just to give you an idea, if sigma is equal to 0.6, it means that you are considering a broad distribution of metallicities. And if you remember, metallicities define the maximum mass of a black hole, means that you have, if you have like a broader distribution of metallicity, you have also like more massive black holes. And with the isolated formation channel, you can get black holes that are more massive, and so close to what you can get with the dynamical formation channel. So the take-home message here is that constraining a mixing fraction is not easy at all, because you do not have just the component on the how you evolve your black holes in your simulation, but you need to couple this evolution with how the universe actually works, and this distribution of metallicity across redshift. Okay, so the hands-on section, you will learn how to use Cosmorate, which is a code that is providing you the redshift distribution of sources. So you will set a population model, and you will define you will evaluate the merge rate density. For example, here I'm plotting one of the results that you can get with Cosmorate. So on the top, you have the merge rate density of black holes, black hole neutron stars, and binary neutron stars, with different values of the alpha parameter that I told you about before. And the gray boxes are the merge rate density estimated with LIGO Virgo. So what you're going to do is to evaluate this quantity. So today, hopefully, you learned what kind of observation we extracted from what kind of properties the observed population of sources has, and you learn how we can model astrophysical gravitational wave sources through the isolated and the dynamical formation channel. Tomorrow, I'm going to talk to you about multi-messenger astrophysics, where we couple gravitational waves and electromagnetic detection. And this will be the perfect place to talk about host galaxies and how we model host galaxies and how we model the chemical homogeneous of the universe that has a huge impact on the rates and the host galaxy properties. I leave you with further readings. Here I'm putting some references on the non-parametric models that you can use to interpret gravitational wave observations. And if you're curious to know more about the astrophysics of compact objects, I leave you with references that are going to go into the details of all the astrophysical processes. And see you later or this afternoon.
If you know you're asking questions, come sit closer to the speaker.
Sorry. So how hard it is to estimate the rates of merge through the channels you presented?
You're asking what are the main source of uncertainty?
I mean, because if they were just to coalesce, I would take the age of the universe, or comparable to the age of the universe, then you showed processes that could catalyze this thing. So at the end, what's the actual time of coalescence?
Oh yeah.
Through
Tomorrow I'm gonna show you a plot of the so-called delay time distribution, which is the time that takes for massive star to merge with each other. Probably I can also show you. Let me. No, we don't need this. Tomorrow we are going to talk about it extensively of this result, but here just because you asked, if you have patience. Okay, so this is the what you are asking basically. The delay time is the time elapsed between the formation of the two massive stars and the actual merger of the two black holes. So basically the age of the universe is on the right, and you see that most of the sources tend to merge soon, basically, below 10 to the minus 10 to the 8 years. And the delay time distribution has this shape of t to the minus 1, kind of this shape, which is the gray line that I'm showing here, and plotting the results of different alpha parameters. So this is just to say that this distribution depends on the astrophysical processes that let those black holes merge.
I have a quick question. So the feature in the mass distribution, no? That is not impacted by the combination of model, isolated binary
yeah. So basically, you are talking about the.
Because that's the most striking feature that LIGO has shown so far, no? That's the most unexpected. That you don't have a simple power law, but there is this extra peak.
Yeah, so basically this extra peak is usually interpreted to be connected with the isolated formation channel. It is sitting between 35 and 40 solar masses. So basically this is an effect of binary evolution. So what we think is that if you go through the common envelope phase, and if you are dealing with more massive stars, you tend to merge them before the common envelope phase ends. So, and you have this pileup of black holes because you are filtering these black holes with this common envelope effect. I don't know if I answered your question. Of course, if you go. This mass distribution is defined in the Payne instability mass gap, and you have a tail going up to 80 solar masses, as in this case. And then the simple interpretation is that, of course, to interpret this, you need at least 2 formation channels. But you can further complicate your picture if you take in account IgN formation channel, hierarchical formation channel, chemical homogeneous formation channel. So you can further complicate the picture of this mass distribution.
Okay.
Hi, Filippo. Thank you for the lecture. I have maybe it's a bit more of a request for commentary on the mixing fraction that you mentioned at the end. So I'm glad to see this as a way to simultaneously account for different information channels in modeling the physical population, because we wouldn't expect just one channel to yield the population that we observe. But of course, we have more than 2 channels. You mentioned a few of them, like triple evolution and chemically homogeneous evolution. Are we at a point where we could hope to account for all of them, or for more than 2 of them simultaneously, or do you think that's too much to ask for at the moment, given the precision of the models and the size of the sample?
So I really suggest you to have a look at this So what we did like couple of years ago, we took in account just 2 formation channels. But in this paper here, Zavin and collaborators 2021, they wanted to have the full picture that you were talking about. They took in account the hierarchical formation channel, GN formation channel, chemical homogeneous, if I'm not wrong. Then they separate black holes forming through the common envelope and through mass transfer, because so they also try to find the mixing fraction of sub-formation channel of the isolated formation channel. The take-home message of that paper is that there is no one dominant formation channel. So you cannot explain all gravitational waves with just one formation channel. But actually constraining this mixing fraction is something that we are not able to do right now.
But maybe something that we could do by looking at specific kinds of mergers that maybe just one or a few channels would be efficient at producing.
Either you have like merger with like so striking signatures, for example, GW190521, the one that it sits in the pairing stability mass gap. This is telling you need to take into account something else. Either you have something like that, but these are also rare events. So I mean.
Okay, thank you.
Yeah. Last question.
My question is about the nature of the envelope. Hi. I didn't have that. I'm not clear about the origin of the envelope. It's like the chromosphere of the photosphere of one of the stars,
okay.
or something like that.
So this is like in the simplest possible way. If you want to model a star, you have like a massive core, and whatever is not this massive core is called envelope. So this is like the simplest way to see it. Of course, like so basically all the layers above this of the core makes the envelope of the star. That can be lost and form the common envelope phase.